In this video, we're going to talk about something called doubling time and half-life. So if we are talking about something that grows exponentially, the doubling time will be the same throughout the whole lifespan of whatever it is that we're talking about. So we could be talking about starting from time t equals 0 and then looking from there how long it would take something to double. But we could be looking at any time and how long it would take for something to double. And the thing about exponential growth is that doubling time is going to be the same throughout the whole entire problem, which is kind of cool. That has to do with the whole proportionality of the rate of change. So let's find a formula for doubling time. So what we're going to do is we're going to start with our formula for exponential growth, and we're going to let capital T be the doubling time. So at time little t, we know that this equation represents the amount present. Y is the amount present, and to actually calculate it, we use this, where t is just some time. So if we look at capital T units after time little t, doubling time would be however long it takes for y to be doubled. So now instead of just y, we're looking at doubling it, 2y. Instead of just time little t, we're looking at capital T units later. And so that's why I'm doing little t plus big T right here. So y will be doubled t units later. And then we're just going to take this equation and solve for t. And so I would encourage you, if you haven't already peeked at the notes, try it on your own, see what you can get. I'll tell you, it ends up being a pretty simple formula, even though this looks like a pretty nasty equation to solve for big T. But give it a shot and pause the video. Okay, hopefully you pause the video and try this on your own, but let's take a look at it. So this is it right here. This is what we had up above. Now I'm just first distributing the k across the exponent, and then doing that same trick we did before when we were solving the differential equation. If I have addition in the exponent, I can split it up into two factors. Multiplying with the same base, you would add the exponents to get back up here. So now I have this. But remember this right here, that is our formula for y. That's our exponential growth formula. So I can take this whole thing and just replace with y. And now I have a y on both sides. So I can divide that out, and I have this. And now it's much easier to solve for capital T. If I take the natural log of both sides, I wind up with this, and just divide by k, and I wind up with this. And there's your doubling time. And by the way, what if doubling time is the natural log of 2 over k, what do you think tripling time or quadrupling time would be? And if you're thinking tripling time is the natural log of 3 over k, quadrupling time would be the natural log of 4 over k. Ah, you're thinking right. So yeah, that's doubling time. This is our formula for doubling time. So a nice simple formula. Now, if doubling time is this, what do you think halving time would be? The amount of time it would take for something to be cut in half. And by the way, that's basically what we call half-life. Half-life is the amount of time it takes for the amount present to decay. So if this is doubling time, what do you think a formula to find the half-life time would be? And if you want to try working it out on your own, you know how I feel about that. Pause the video, give it a shot, but let's take a look together. All right, so this time we're talking exponential decay, so I am going to put the negative here. And we're going to let capital T be the half-life. So this time we're talking about capital T units later, we're going to have half the amount present left. And then we'll do the same kind of thing we did before. I'm going to just distribute the negative k, and I'm going to split it up into two factors. Again, when you multiply with the same base, you can just add the exponents, so this works. Here is our equation for y, right up here. And then we can divide the y out, and we get this, and take the natural log of both sides, you get here, and then all we have to do is just divide by t. And there's our formula. But hey, wait a minute. Can't we do something a little more with this? And yes, we can. If I move this negative as an exponent to the log, then I just raise the argument to the power of -1, and whoa, look at that. I get the same formula as doubling time. How is that possible? Does that even make sense? And the answer is, yeah, it does. Of course it does. Now, again, try to think about why that makes sense. Why would the formula for doubling time be the same exact formula for the half-life time? And try to think about it on your own. Pause the video, and here we go. Okay, so essentially, I'll try to make this, there we go, that fits the screen. Um, so why is it the same? Well, we have this formula and this formula. This is for exponential growth, this is for exponential decay. But take a look at the formulas and think about transformations. They are the same function. The negative is just going to reflect about the y-axis. So you would have something like this that would be exponential growth, and you would have a curve like this that would be exponential decay. Now, if we take a look at this one, this graph, going forward, things are increasing. So the amount of time it takes something to double going forward, if we move backwards, it would be the same amount as having something. So, for instance, let's just say that we started from here with this much, and we want to double it, and we go here. So if I go this way, that's the amount of time it took it to double. But if I go this way, that's the amount of time it took it to be cut in half. It's the same amount of time. And then you would have the exact same thing here. It's just backwards. This time going forward is the amount of time it would take for something to be cut in half. Going backwards would be the amount of time it takes for something to double. So it's really just because of the symmetry of the graphs. And that, going forward, you're doubling, going backwards, you're halving, but it's the same amount of time. So it does make sense that they're the same. All right. That is the end of this video.